Today, we're not just diving into physics, we're cracking open a case file on one of the greatest detective stories in the history of science, the epic, centuries-long hunt for the true identity of light. At the very heart of this mystery is a question that seems simple, but it's stumped the greatest minds for ages. What is light? Is it a spray of tiny, invisible particles like little bullets, or is it some kind of ripple moving through space? The answer, as they were about to find out, would change everything we thought we knew. Okay, so let's set the scene. Back in the 17th century, the scientific world was basically split into two camps, led by two absolute giants of the era. Each one had a completely different idea about what light was. So in one corner, you've got Sir Isaac Newton. His theory? That light is made of tiny particles he called corpuscles. And, it was a pretty great theory. It explained why light bounces off mirrors and why it bends through a lens. But in the other corner was a Dutch physicist, Christian Huygens. He argued, no, light is a wave, kind of like the ripples in a pond. And his theory also explained reflection and refraction. So how on earth could you tell who was right? Well, it all boiled down to one single critical disagreement. Newton's particles had to speed up in water. Huygens's waves had to slow down. One of them had to be wrong. And what's wild is just how long this argument went on. For more than 100 years, Newton was such a big name that pretty much everyone just went with his particle theory. But then, in the 1800s, two crucial events happened that were about to blow the case wide open. The first big break in the case came in 1801, and it was all thanks to a British physicist named Thomas Young. What he did was so simple yet so profound, and it gave us the first piece of undeniable evidence that light was doing something particles just don't do. This was a huge moment. Now, before we get into his experiment, we need to understand one key idea: coherence. And the analogy for this is perfect. Picture two needles tapping the surface of a pond. If they're tapping in a perfect, identical rhythm, up and down, exactly in sync, the waves they create are locked in phase. They have this stable, predictable relationship. And that idea is the whole secret to what Young did next. Young's setup was just genius in its simplicity. He took a single light source, passed it through one tiny slit to make a nice, clean beam, and then he aimed that beam at a screen with two more tiny slits right next to each other. By doing that, he basically turned those two slits into two new light sources that were perfectly in sync, just like our two tapping needles. They were coherent. So here's the million-dollar question. What did he see on the final screen? I mean, think about it. If light is just a stream of tiny particles, like little paintballs, you'd expect to see two bright lines, right? One for each slit. Makes sense. But that is not what happened. Not even close. Instead of two lines, Young saw this totally bizarre pattern, a whole series of bright and dark bands, almost like a barcode. This pattern, these interference fringes, it was a complete bombshell. It made absolutely zero sense if light was a particle. But if light was a wave, well, then it was the smoking gun. You see, this is what waves do. It's called interference. When the crests from both waves arrive at the same spot, they add up and make a super bright spot. That's constructive interference. But when a crest from one wave meets a trough from the other, they completely cancel each other out, leaving a spot of total darkness. That's destructive interference. A pattern of light and dark created from two light sources. Only a wave could do that. This kind of interference pattern is a classic sign of a wave. It's tied up with another effect called diffraction, which is just how waves tend to bend a little when they go through an opening. Even the great Richard Feynman said the line between the two is kind of blurry. But here's what's crystal clear. Particles don't interfere, and they don't diffract. This behavior is the unmistakable fingerprint of a wave. Okay, so the double slit experiment was a massive win for the wave theory, a huge point for Team Wave. But could the wave theory also explain the everyday stuff, like reflection and refraction, as well as Newton's theory did? Well, for that, let's turn to Huygens' principle. Huygens came up with this really elegant, beautiful way to predict how a wave would move. Basically, he said to imagine that every single point on the edge of a wave is creating its own tiny circular wavelet. The next position of the main wave is just the line you can draw that touches the leading edge of all those little wavelets. It's a simple geometric trick. And what's so cool is that using this one simple idea, you can perfectly prove the law of reflection. No problem. It just works.
The wave model passed that test with flying colors.
And here's where it gets really important, because this brings us right back to that big showdown with Newton. When you use Huygens' principle to figure out why light bends when it goes into water, the math makes one thing absolutely clear. For it to work, light must travel slower in water than it does in air. It's not a suggestion, it's a requirement of the model. And then, in 1850, the experiment was finally done. Leon Foucault managed to measure the speed of light in water. And, wouldn't you know it, it travels slower, just like the wave theory predicted. Huygens was right. This was another nail in the coffin for the particle theory. So at this point, the case for light being a wave is looking pretty much rock solid. The evidence is just piling up. But there was one final discovery that would not only confirm it, but would also tell us exactly what kind of wave it is. It was time to finally uncover light's secret identity. To get this last clue, let's go back to a simple analogy. Imagine you're shaking a rope up and down to make a wave. The wave travels forward, but the rope itself is moving up and down, right? That's a transverse wave. Now, if you try to send that wave through a vertical slot, like in a picket fence, it'll go right through. But if you turn the slot sideways, horizontally, the wave gets completely blocked. Well, it turns out you can do the exact same thing with light using special filters called Polaroids. A Polaroid filter acts just like a set of molecular slots. If you take two of them and you turn the second one 90 degrees to the first, the light gets blocked. This effect, called polarization, is the final proof. It proves that light must be a transverse wave, just like the wave on the rope. Its vibrations are at right angles to the direction it's traveling. So, let's recap our detective story. Let's look at the evidence file. We have interference and diffraction from the double-slit experiment. We have the correct explanation for refraction, proving light slows down in water. And now we have polarization, proving it's a transverse wave. All of these are smoking guns, and they all point to the same suspect. And there we have it. The mystery, it seemed, was solved. By the end of the 19th century, the scientific community had reached a verdict. Light is a transverse electromagnetic wave. Case closed. But you know how in every good detective story there's that one final twist at the end? Well, physics has one of the best. Because just when everyone was sure, new clues from the 20th century started to reopen the case, revealing a reality that was way, way stranger than Newton or Huygens ever could have dreamed of. A world where light was somehow both a particle and a wave at the same time. But that is a whole other story for another day.